Hello everyone. So again welcome back to the latest lecture session. So we have been discussing the relevant aspects of risk assessment, right? And in that context we looked at why risk assessment is relevant or necessary, and we looked at a few what do we say, corollaries out there, I guess, or analogies, pardon me, right? And then we started looking at risk assessment in greater detail. So risk assessment obviously looks at four major aspects. So one is hazard identification and data collection. The second aspect would be toxicity assessment, or looking at the dose response behaviors, right? And then looking at exposure assessment, and then bringing all these three aspects together with respect to risk characterization, right? So these are the four major aspects of risk assessment. In that context, we were already done with looking at briefly the relevant aspects with respect to hazard identification, right, and data collection. And then we moved on to what is it now, toxicity assessment and dose response behaviors and such, right? In that context, we looked at why we need to look at toxicity assessment in greater detail, right? Though we do have the relevant what do we say, variables or the numbers given out there in the relevant databases, it's because there are considerable uncertainties involved. So it's worthwhile obviously to look at the relevant aspects, I guess, right? So in that context, we moved on to what do we say, generic example of dose response behaviors, right? So here we have that particular aspect here. So with increasing doses, as you see increasing adverse responses, right? It can be carcinogenic responses, right? Or it can be any other non-carcinogenic responses to it. It can be something as simple as hair fall, let's say, right, or damage to the kidney and such, right? Not as simple as that though, right? So again, so cancer, typically we assume that it's linear at the relatively low doses. We are going to look at that in greater detail. So for the other aspects, though this is a generic figure, this is typically not the case. We are going to again look at this in greater detail, right? So again, typical aspects, I guess. So here for carcinogens, right, what are the aspects? As in, I have my data only in this range, I guess. So let's say from my particular experiments on the animals or animal studies, let's say, at different doses, right, at different doses, these are the responses or carcinogenic responses that were observed, right? So again, as we looked at it earlier, understood it earlier, typically, right, how do we go about conducting these trials? Let's say we accelerate the trials, right, at shorter periods. We want to get it done within a shorter period of time, not we, the relevant people, I guess, right? And obviously to try to get to that relevant aspect, they increase the doses, right? They increase the doses by quite a few orders of magnitude from case to case, I guess, right? So obviously we have data only at higher doses, right? But obviously in general though, we as in humans are rarely exposed to concentrations at these levels of doses that we administer to the animals, right? So how do we extrapolate the data? So in that context, let's say, so here let's say there are different possible what do we say patterns, as in it could be this particular pattern, right, extrapolation by this particular model, or the yellow model or the blue model, right? But typically though, they go for the linearized multi-stage model or multi-stage linearized model, let's say, right? And here they assume or take the most conservative estimate that even at low doses, right, it's the response between what do we say, the behavior is linear between the dose and the response, right? So even at very low doses, right, even at very low doses, we assume that there is always going to be some carcinogenic response, right? So that's the key aspect with respect to carcinogens. And again, linearized multi-stage model. So here I have some actual data. So looks like these are the data points from the experimental doses or animal experimental doses, right? And here they came up with a particular model now, right? So this is the solid line based on the fitted data, right? But obviously they are conducted as in the animal studies are conducted at relatively high concentrations, as you can see. I believe this is logarithmic scale, as you can see. So obviously there are different models, right? Again, this is where some uncertainty lies, but typically people assume that this linearized multi-stage model is what do we say, relatively conservative model, right? Again, here the key is that even at low doses, we assume that there is going to be some adverse response, as you can see out here, right? So that's one particular aspect in that particular context, right? So let's move on. So here let's say carcinogens are classified, right? And typically we look at the US EPA classification. So here we have 5 different classifications, and here is the reference category, as in depends upon the level of or weight of evidence that has been gathered thus far, right. So, in that context, A, the highest class, human carcinogen, as in it has been known to cause cancer in humans, right. So, that is the highest class. In B, there are again two classes, B1 and B2. So, it is classified as the compounds that fall under category B are classified as probable human carcinogens, right. B1 indicates there is some limited human evidence, and B2 indicates sufficient evidence in animals, but inadequate evidence or no evidence in humans, right. So, obviously B1 relatively higher and B2 relatively lower, as in B2 we do have what do we say confirmation that the relevant compounds at the relevant exposures, let us say or relevant doses cause cancer in the animals, but there has been limited as in no studies might have been conducted, right, or studies might have been conducted and it's there is no evidence, let us say, that the relevant compound has caused cancer in humans yet, right. So, again that is B, and then C, possible human carcinogen, D, not classifiable as to human carcinogenity, and E, there is no evidence, right, as in after testing there is no evidence of carcinogenicity in humans, right. So, different classes, again this is something we need to be aware of, right. So, here we come back to the non-carcinogens. Earlier we looked at the carcinogens, right. What did we look at there? We have the dose and response here, and let us say irrespective of what the, let us say for example, this is the model, let us say from the data that was actually observed from the animal studies, but we assume that for carcinogens at the lower doses it is going to be a linearized model or linearized multi-stage model, I guess, linearized, and we have two stages or different stages or multi-stages, linearized multi-stage model, right. But for non-carcinogens, as you see, right, there are different aspects, as in these are the data points here, right, these are the data points, again dose versus severity of this particular adverse response. So, we have different data points from the animal studies here, right. So, let us look at how this is going to this as in the dose response behavior for non-carcinogens or just the toxic compounds is going to differ from how we look at or try to extrapolate the relevant effects from or for the carcinogens, I guess, right. So, here as you see we assume that there is a threshold level, as in we develop the model based on the experimental data, and that there is a threshold, right, as in below this particular threshold, if the dosage is below this threshold we assume that it is relatively safe. So, above that there are going to be adverse effects. So, there is some sort of a reference or zero dose, if you not zero, pardon me, a safe dose, I guess, right, in the context of non-carcinogens. So, in this context there are 2 or 3 terms that we need to look at other than threshold. One is the lowest observed adverse effect level or LOAEL. Again I repeat, it is the lowest observed adverse effect level, right. So, obviously it is self explanatory. What does it mean now? What is the lowest concentration? As you see, this is the lowest concentration at which some adverse effect has been noticed, right. So, that is the lowest observed adverse effect level, and then we have NOAEL, which is the no observed or no observable adverse effect level. So, what is the highest concentration, right, and this is the highest concentration at which no adverse effect was observed, right. So, NOAEL and LOAEL. So, obviously the more the data you have, the better that you would the better kind of data that data that you would come up with that can be used for better estimation. So, depending on are we going with LOAEL or NOAEL, obviously there are going to be uncertainties. So, we are going to again look at these aspects. Again, what is the take home message? And for the non-carcinogens, it is that we assume that there is a safe dose, right. Unlike the cancer or carcinogens, where we assume that even at low doses we assume that there is a response, but we see that that is not the case out here for the non-carcinogens. And then we came across 2 terms, LOAEL and NOAEL, right. So, again we are going to move on, let us say. So, here obviously we are need to calculate this safe level, right. How do I calculate this safe level, right. So, it depends upon dividing the LOAEL or NOAEL that we just calculated and dividing that by different uncertainty factors, right. Again LOAEL, lowest observable adverse effect level, no observable adverse effect level. So, we discussed this, so we are not going to go into that. So, how do I, so here as in safe level, how do I come about that? The safe level here that we are referring to refers to the safe level for the humans now. So, here we are trying to, what do we say, estimate the safe level in the humans based on the relevant experiments or studies on the animals here. So how do I do that? Dividing the LOAL or NOAL by some safety factors or uncertainty factors. So let's look at what they are, right? So 10 for human variability, as in, let's say my what do we say, response to being exposed to a particular carcinogen or toxic compound would be different to what your response would be, right? So different people, again, let's say pregnant ladies, women, the elderly people, and so on, there will be variation from human to human. So for that particular aspect, we look at 10 or consider 10 to be one uncertainty factor, and certainly again 10 because obviously we are trying to, what do we say, estimate the effects on humans based on animal studies, right? So thus obviously we have another uncertainty factor that we take into account, and 10 for less than chronic data, right? As we discussed earlier, right, we are trying to look at accelerated trials, right? We are trying to estimate the, what do we say, effects based on, what do we say, conducting the trials at over lesser time ranges at higher doses, right? So obviously again there are going to be some such issues. So if it's not chronic data, let's say, and then again for that case we are going to use 10, and if obviously here this is another context we discussed slightly earlier. So I'll use another uncertainty factor of 10 if it's I'm using LOAL instead of NOAL, right? So LOAL again, right, if I look at this particular aspect, see, if I use LOAL, right, if I do not have this data point, this would have been my LOAL, right? So here it's always better to have data on NOAL, right, NOAL rather than LOAL, because depending upon the limitations of your particular study, your LOAL could be pretty high, right? Then that would lead to, what do we say, underestimation of the adverse effects, or underestimating the, or overestimating, let's say in this context, the safety level, I guess, right? So obviously if I have only the LOAL and not the NOAL, I need to have an additional what do we say, safety factor or uncertainty factor, right? So from that I am going to be able to calculate my safe level for the humans, right? And some major assumptions, I guess, right? What are they? So we are always trying to try to select human data over animal data whenever we have such data, right? And use animal data obviously only when human data is inadequate, and usually we look for the one that has, we are trying to estimate something. Obviously you need to have a relatively good correlation between what you observe and what you are trying to estimate, right? So obviously we are going to select the most sensitive animal species or strain, that's a different aspect obviously. So and then apply uncertainty factors to scale between species, right? And again linearized multi-stage model for low dose extrapolation, and this obviously we talked about in the context of carcinogenity, right? So linearized multi-stage model. So again I mean just a example here, I guess. So let's say 1 million people jump from a height of 100 meters. So let's say assume 900,000 or 9 lakh people die. So 10 lakh people jump, 9 lakh people die, let's say, and let's say if people, the same 10 lakh people jump from 10 meters, 90,000 are going to die. Again here we are just trying to illustrate the linearized multi-stage model, I guess, and why it's relatively conservative, relatively. So again if I then what does that extrapolate into? So if 10 lakh people die from 1 meters, it assumes that still 9,000 people are going to die, and it again assumes that even if 10 lakh people die from, let's say, what is it now, 1 mm height, I guess, right? Is it 1 mm? I assume so, right? 9 people are going to die, right? So you see that there is a built-in, not built-in, let's say, this linearized multi-stage model. What does it assume? That there is going to be an adverse effect, which is death in this case obviously, I guess, even at very low doses, right? Even at very low doses we assume that there is going to be some adverse effect, right? So again some relatively conservative what do we say, estimation. And why is that? Because we are looking at cancer here, right? Again moving on, so we looked at hazard identification and data collection, and then we looked at toxicity assessment and dose response curves or behaviors, and then it's the exposure assessment, I guess, right? What exposures are experienced under these conditions or different conditions, as in how am I exposed to the relevant agent, right? So human exposure evaluation, so what do I need to know? Where is the agent found, right? In my particular the receptor, I guess, right? What are the routes of exposure? Or am I exposed through the air pathway and then I am going to inhale it, or is it deposition on the soil and then I am going to have dermal contact with the soil or ingestion of the soil. So what are the routes of exposure? How many people or what is the level of population that is being exposed? Who is exposed, right? Is it what do we say healthy, what do we say humans, or is it infants, or let us say elderly people who are more susceptible? So what kind of population is being exposed, right? So and then more importantly, what is the intensity, frequency and duration, right? So we are going to look at why this is relevant in the next slide, I believe, right? Again, I guess we have some other aspects. So again, looking at the pathways, so this is the source, right? Different modes of transport, right? Through the air, surface, groundwater or soil, right? And then while breathing personal air or from tap water, food or household, and then routes of exposure, inhalation, ingestion and dermal, right? These are the different pathways. Obviously that is an illustration out here. So here if we consider an example of, let us say, emissions from a particular factory now, what can happen now? You are going to have, let us say, concentrations of different contaminants in this particular plume outside in the atmosphere, and then you can have wet and dry deposition that can, what do we say, have lead to ingestion or dermal contact, or you can directly breathe the particular contaminated air and then that leads to intake, right. So we just looked at one example as in to look at or understand the different pathways at play here. So we are talking about air pollutions or emissions from particular industry, and you have, what do we say, the relevant contaminant traveling through the air over a certain distance, and then I end up either breathing the air directly, which is inhalation directly in this case, right, or there can be deposition of the contaminant, wet or dry deposition onto the soil, and different pathways, let us say, as in dermal contact or ingestion of that particular soil, let us say, or water, let us say, and then leading to intake of the relevant compound, right. And then obviously I need to look at risk characterization. So in this context, as I talked about earlier, the exposure, let us say, depends upon intensity, frequency and duration, or in layman's terms, how much am I being exposed to, how often am I being exposed to, and how long, right. So based upon all the data that we have at this until this stage, we can come up with this exposure assessment, right. How much am I taking in, right, how often and how long, how much, how often and how long, right. Again, the uncertainties here are, obviously you are going to estimate some of these variables. You can have detailed studies, but in general you are going to have to estimate some of these variables, and again that is where the uncertainty again creeps into the picture, right. Again, obviously as we talked about, characterization of the exposure setting, as we just looked at one example, identification of the exposure pathways, and then quantification by these particular set of, what do we say, formulae. But here we have the generic formulae, right, where the intake depends upon the exposure concentration, intake rate, exposure frequency, exposure duration, and body mass or body weight, and average time in the denominator, right. Averaging time would be the exposure duration if it is for non-carcinogens, right. For carcinogens though, the averaging time will be equal to the lifetime, because we are looking at lifetime cancer risks, and lifetime is typically assumed to be 70 years, right. This is something that you need to keep in mind. So again, as I mentioned, this is the generic formula. So for different kinds of intake, as in soil ingestion, air inhalation, water ingestion, dermal contact and such, you have different other what do we say, variables coming into picture, but here obviously you have the relevant aspects with respect to how much, how often and how long, I guess, right. These are the aspects here, and based on this I am going to be able to calculate the rate of intake of that particular compound. And what are the units? The mass of the contaminant per mass of body weight, or per unit mass of body weight per time, per day, I guess, milligrams of the contaminant per kg of body weight per day, right. So let us move on, and once I have these relevant aspects, obviously as in hazard identification, I am done with exposure assessment and then dose response, I can come up with risk characterization, right, as in what is the likelihood or probability of adverse effect, or what is the likelihood or probability of this target population, facing an adverse effect, I guess, right. So that is something we can get from the risk characterization, right. How do I do that again? For, let us say, for non-carcinogens, I can calculate the hazard index, right. That is going to be equal to the intake that you calculate by the reference dose, right. and for carcinogens I am going to calculate the lifetime cancer risk, that is going to be equal to the intake into the slope factor, right. And slope factor again, how do I get that? As you see there from the dose response curves and such, I can get the slope factor, dose and response, right. And reference dose, how do I get the reference dose? As we talked about earlier, reference dose either L or NOAEL by the uncertainty factors, right. So, for non-carcinogens and for carcinogens, right, intake into slope factor for lifetime cancer risk and intake by reference doses for hazard index. The summation of all the hazard index for different compounds and different pathways, we look at it as hazard quotient. So, if it is greater than 1, that means it is unacceptable risk. For lifetime cancer risk, the risk should not be greater than 10 power minus 6. Some cases people look at 10 power minus 4, but typically it is 10 power minus 6. Hazard quotient should not be greater than 1, sum of all the hazard indices, pardon me, and lifetime cancer risk should not be greater than 10 power minus 6, right. So, again we are going to look at an example soon. So, again what do we have here with respect to risk characterization? All the three aspects, as in hazard identification, assessment and dose response, we bring all these aspects together, right, and then obviously we come up with risk estimates, as we talked about the hazard quotients and the lifetime cancer risks, right, and then we need to communicate the significance of the risk, and more importantly though we need to give an idea about the assumptions and uncertainties here, right. As in just giving out numbers, let us say, right, while it will serve some purpose, we always need to understand that there are considerable uncertainties that are at play here. So, in that context, obviously when you are presenting the results, you need to present what are some of the gray areas out there, right. So, that is something that we need to look at with respect to risk characterization, right. So, I believe we are now going to look at a particular example from a particular landfill site. So, here we are going to present some data, let us say as in a few people working at the particular landfill, let us say, and we are going to look at the relevant data and we are going to calculate these particular variables here. So, before we go further, what are we going to calculate? We are going to calculate the average daily intake, right, which is relevant to exposure assessment, I guess, right, and we are going to calculate the maximum hypothetical intake, right. So, these are the two aspects that I am going to look at obviously, and also we are going to then move on to calculate the total carcinogenic and non-carcinogenic risks, right. But the key aspect here is that it is from ingestion of soil. So, we are not looking at all the pathways as in from inhalation or from air or from ingestion of water or such though. I am only looking at soil in this particular aspect, right. But obviously if I am trying to calculate the hazard quotient or such, obviously I need to calculate all the different pathways for all the different compounds, but for this particular example we are looking at, we are obviously only looking at the soil pathway, right. So, here what are some of the data that I have? Here I have different pathways: air, groundwater, soil, right, and I have the different compounds here, right. So, let us say this is my hazard identification and what do we say now, data collection. So, let us say I have this particular set of data now. So, obviously though I am not concerned with these sets of data, I am only concerned with these sets of data because the question that we are looking at, our example only wants to look at or understand the effects from soil ingestion, I guess, right. So, moving on, what do I need to do? I need to come up with the relevant formula for soil ingestion. As I mentioned, it is slightly different from the generic formula, right. So, here we have different variables out here, again these are formulae that are going to be given out. So, here we have intake, which is what we are going to calculate, both the average and maximum, right. This is what we are trying to calculate. So, Ce is the exposure concentration in the soil, milligram per kg, which is what we already have out here, right, which is the mean and maximum, we are going to consider both. And then soil ingestion rate at which soil is accidentally ingested, we are going to have some standard values here. The conversion factor from kgs to milligram, 10 power minus 6, and fraction of ingested soil, that is from contaminated site. And here I guess we are going to go with the conservative estimate and take it to be 1. And exposure frequency, right, again it depends from case to case, and here we are going to choose a particular value. We can either choose, let us say people are working for 5 out of 7 and so on, 5 days out of 7 days and so on, for exposure duration, let us say exposure frequency, pardon me, and so on. Exposure duration, I believe we are going to look at it for over one period, 1 year. Body mass, we have what do we say, some standard values, and averaging time, as we mentioned, averaging time is going to be equal to exposure duration for the carcinogenic, pardon me, for the non-carcinogenic risks, and averaging time is going to be equal to lifetime for the carcinogens, right. So, obviously what does this mean? If averaging time differs, that means we are going to have two different intakes, one for non-carcinogens and one for carcinogens, right. So, let us move on. So, here what are the different values? I think this is the rate of soil ingestion rate, it is 10 power minus 6 kg per mg. Fraction of soil that is from contaminated site, we are taking it to be 1. Based on the relevant site conditions, looks like we are going with exposure frequency to be 156 days per year, or as I mentioned earlier, we can assume that out of the 7 days in a week, people are going to work for 5 days and take it to be 261 days per year. Obviously this particular aspect would depend upon the relevant site. And then we have exposure duration, for that particular site we are looking at 1 year. Body weight, from the standard table we are taking 70 kgs. So, again this is where the uncertainties creep up into the relevant what we say analysis, as in body weight, my body weight might be different or certainly is different from 70 kgs, your body weight will be different and so on. So, how do I put a particular number on this? So, in this case obviously we are looking at the standard values, and again these are the uncertainties that come into picture now. So, averaging time, as I mentioned, is equal to exposure duration for non-carcinogens, right, that is 365 days, and for carcinogens it is equal to the lifetime, which is 70 years, right. So, we have two different values, and I believe we calculate the relevant intakes, right, based on both the average intake or average concentration and maximum concentration. So, here we have the average intakes and maximum intakes, right, in milligrams of compound per unit or per kg of body weight per day, right. We have these two aspects and we calculate the intakes. Why do we say for non-carcinogen? Because the averaging time is different for non-carcinogens and carcinogens, and again for carcinogens we end up having different levels of intake for the different compounds, right. So, again just calculating the intakes obviously does not convey the relevant information to me, right. So, what do I need to look at or consider now? So, obviously I need to consider the toxicity assessment, and what is that about? That means I need to look at the reference doses and the slope factors, right. So, let us look at what they are. So, slope factors again from the standard data. So, looks like these are the slope factors not available. So, let us say in that case I am going to assume that chlorobenzene and 1,2-DCA are not carcinogens, right. Only chloroform and BHP are carcinogens, because I have the slope factors only for those two particular compounds. So, then risk is equal to the intake into slope factor, that is what we have, and we are going to calculate the relevant risks. And let us see what we have here. So, risks, and based on the average concentration that we had in the earlier table. So, for chloroform this is the level of risk from soil ingestion, and for BHP this is the level of risk from soil ingestion, accidental soil ingestion. So, the value turns out to be 1.3 into 10 power minus 8, right, the risk, the total risk anyway, posed to the person working there for 1 year at a frequency of either 260 days per year or 150 days per year. I think we took 150 days per year in this context. At the given rate of ingestion for a person of that 70 kg body weight, the what do we say, the risk based on what is it now, the carcinogenic risk would be, or the cancer risk would be what now, 1.3 into 10 power minus 8. So, this is less than 10 power minus 6. But obviously the conclusions need to be tempered by the fact that there are uncertainties involved, and more importantly that we are only looking at one pathway, which was soil ingestion. We have not looked at groundwater or air inhalation, right. So, again with respect to one pathway though, yes. So, same case we are going to move on to the non-carcinogens or the toxic compounds, and these are the reference doses, right, RFD as we mentioned earlier. And again these are the standard values, let us say, and looks like 1,2-DCA is not a toxic compound, probably only a what is this now, carcinogen. No, looks like 1,2-DCA is neither a carcinogen nor a toxic compound, at least in this particular set of data that I have. So, I have the reference doses for different compounds, right. Again, keep in mind that a particular compound can have both toxic effects or non-carcinogenic effects and also carcinogenic effects, and that is why we have some such data here. And then what do? I end up calculating the hazard index now, right. How do I calculate the hazard index? As I have it out here, hazard index is going to be equal to intake by reference dose, and the intake again is for non-carcinogens, right. So, calculating that, I have the hazard index for different particular compounds. Looks like there is a greater risk from BEHP compared to chlorobenzene and chloroform, and the total hazard index, let us say, or hazard quotient, let us say, for soil ingestion anyway, is 3.3 into 10 power minus 3, and that is less than 1 though, right. Again, 1 is obviously the threshold we are looking at, as in which is the acceptable value. But obviously here, the again similar to the lifetime cancer risk or cancer risks, we need to consider the fact that we are only looking at the soil pathway, right. So again, this is how I guess this helps you understand the relevant aspects. So maybe in the next session, we are going to look at the risk from air and groundwater, those two pathways too, for both the carcinogens and non-carcinogens, and then we can compare which pathway poses the greater risk to the relevant population out there or the exposed population, and then we can look at the relevant remedial measures, I guess, right. And I guess with that I am done for today, and thank you.